Summary: atoms are the building blocks of elements. They are the smallest parts of an element that chemically react. The first atomic theory, proposed by scientist John Dalton in 1808, regarded atom as the ultimate undivisible particle of matter. Towards the end of the 19th century, it was proved experimentally that atoms are divisible and they consist of three fundamental particles: electrons, protons, and neutrons. The discovery of subatomic particles led to the proposal of various atomic models to explain the structure of atom. Thomson in 1898 proposed that an atom consists of uniform sphere of positive electricity with electrons embedded into it. This model, in which mass of the atom is considered to be evenly spread over the atom, was proved wrong by Rutherford's famous alpha particle scattering experiment in 1909. Rutherford concluded that atom is made of tiny positively charged nucleus at its center with electrons revolving around it in circular orbits. Rutherford's model cannot account for the stability of the atom, that is, why the electrons does not fall into the nucleus. Further, it was also silent about the electronic structure of atoms, that is, about the distribution and relative energies of electrons around the nucleus. The difficulties of the Rutherford model were overcome by Niels Bohr in 1913 in his model of the hydrogen atom. Bohr postulated that electron moves around the nucleus in circular orbits. Only certain orbits can exist and each orbit corresponds to a specific energy. Bohr calculated the energy of electron in various orbits and for each orbit predicted the distance between the electron and nucleus. Bohr model, though offering a satisfactory model for explaining the spectra of the hydrogen atom, could not explain the spectra of multi-electron atoms. In Bohr model, an electron is regarded as a charged particle moving in a well-defined circular orbit around the nucleus. The wave character of the electron is ignored in Bohr's theory. An orbit is a clearly defined path, and this path can completely be defined only if both the exact position and the exact velocity of the electron at the same time are known. But this is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom not only ignores the dual behavior of electron but also contradicts Heisenberg's uncertainty principle. Scientist Erwin Schrödinger in 1926 proposed an equation called Schrödinger equation to describe the electron distributions in space and the allowed energy levels in atoms. This equation incorporates de Broglie's concept of wave-particle duality and is consistent with Heisenberg's uncertainty principle. When Schrödinger equation is solved for the electron in a hydrogen atom, the solution gives the possible energy states the electron can occupy and the corresponding wave functions, psi, which in fact are the mathematical functions of the electron associated with each energy state. The quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers, principal quantum number n, azimuthal quantum number L, and magnetic quantum number m, arise as a natural consequence in the solution of Schrödinger equation. The quantum mechanical model of the hydrogen atom successfully predicts all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by the Bohr's model. According to the quantum mechanical model of the atom, the electron distribution of an atom containing a number of electrons is divided into shells. The shells are thought to consist of one or more subshells, and subshells are assumed to be composed of one or more orbitals which the electrons occupy. For hydrogen and hydrogen-like systems such as helium plus, lithium 2 plus, etc., all the orbitals within a given shell have same energy. The energy of the orbitals in a multi-electron atom depends upon the value of n and L. The lower the value of n plus L, for an orbital, the lower is its energy. If two orbitals have the same n plus L value, the orbital with lower value of n has the lower energy. In an atom, many such orbitals are possible, and electrons are filled in those orbitals in order of increasing energy in accordance with the Pauli's exclusion principle that states that no two electrons in an atom can have the same set of 4 quantum numbers, and Hund's rule of maximum multiplicity, which says that pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to the subshell has got one electron each, that is, singly occupied. This forms the basis of the electronic structure of atoms.